Hi, this is Kelly Hill, technology reporter for RCR Wireless. I'm here today with Alfonso Rodriguez, who is a senior RF and systems engineer for Spirent, and Derek Skousen, who's technical marketing manager at Bluetest. Gentlemen, welcome.
Thank you, Kelly.
Thank you.
Now, both of your companies are collaborating on a new solution for LTE MIMO OTA testing, over-the-air testing. And I'm wondering if maybe we can start out with a little bit of a description of what that collaboration has resulted in and which pieces come from which company.
Well, I think a lot of this has started from the idea of customers wanting to do more with over-the-air testing. And reverberation chamber technology is something that Bluetest has been introducing to the over-the-air market for a few years now. And it's often seen as kind of a newer technology to this particular usage, even though people have been using reverberation chambers for the EMC market for, oh gosh, almost 30 years now. And as we have been working with this over-the-air community, they keep asking us to do more with the reverberation chamber. A reverberation chamber is basically a big metal box. It's a big metal box that we can put a phone in, and then we'll inject a signal that represents a base station, and the phone will listen to that base station. But inside this box, it's like a little bit of an echo chamber. And the wave fronts are going to be bouncing around and hitting that phone from all different angles almost at the same time. And what that represents is a quick way to quickly see how a phone reacts when it sees microwaves and incoming power levels from so many different directions over time, which is what a real phone experiences as we wander through cities and even more so as we go through indoor applications. What users have been asking us for with the reverberation chamber is this ability to do even more with the environment inside the reverberation chamber. And not just with the environment, but with the actual channel characteristics in terms of time, in terms of correlation, using multiple inputs and to emulate base stations that have multiple antennas, and to really test these multiple antenna systems that represent MIMO. And I can imagine that that Spirent was probably getting requests in the same way from the other direction.
That is correct. So basically, users want to identify the issues that new handsets are having out there. And traditionally, the conducted type of testing has been lacking the part of the antenna. And now, MIMO being a key technology for evolving data rates, then it is key to understand how the antennas in the handset interact with the different electromagnetic fields out there. And for that, nothing beats an over-the-air testing, or simply known as OTA. And in trying to make Derek's explanation more complete, what Spirent brings to the table is added correlation in the base station. So this is a property that stresses a given handset out there, and then this is a key part that our channel emulators are equipped to do. Additionally, we can do higher Dopplers that go beyond the typical Doppler seen by a reverberation chamber alone, created by the mode steerers. And finally, given that the reverberation chamber has a limited delay spread, then the channel emulator can include this impairment as well, and we excel at those three features.
Okay, and it's the VR5 channel emulator that's integrated with Bluetest's reverberation system. Yes.
Yes, that's correct. That's Spirent's flagship of channel emulation.
Okay, great. So let's talk about some of the trends and the challenges here. What are some of the main challenges for operators who are trying to verify device performance for MIMO?
Well, one of the things that we've seen is they are really trying to separate out different kinds of devices and to recognize which devices are really going to work well on their system and which ones are going to be always struggling and asking for more resources from the base station, asking for higher power levels, and in the worst case, dropping their customers' calls on a regular basis or showing really low data performance. They are investing a great deal into the networks now to increase the amount of data in there, and part of that is hardware, part of that is software, and all of those tend to come together in the wireless system, and the phones need to take advantage of all of those network and characteristics in that. So what this creates is it creates a system problem for the phones. You have to test the entire phone system. And when we talk about the system, we're not just talking about the RF chipset on there or maybe what version of the Android firmware that we have running at the moment. It's really the interactions of all of those things coming into at the same time. Not only is it those chipsets and the things that you get when you take off the cover, but in fact, part of the system of a wireless phone is the case design itself. It's even when people put different covers on their phones, and even when they pick up a phone and hold it in their hand and put it up next to their ear, that starts to change and affect the way the phone responds to all of the different microwaves that are around it. So what over-the-air testing allows them to do is put this phone in a place where they can test all of those things at the same time. They can use head and hand phantoms. They don't have to plug into subsets of the device. It's really just coming in over the air like it would in real life. Of course, we need to make that so that it happens quickly and repeatably and accurately. And as Alfonso mentioned, the reverberation chamber test system starts with kind of a basic environment. It's this air environment that has a lot of channel characteristics already built in, and a statistical environment where a lot of things are changing, but we can really accurately characterize how that phone operates on average. And then we need to get to that next level of challenge, which is, how do I really know this phone is better than that phone? And to do that, we really have to push the channel that the phone is working in, and that's what we depend upon Spirent for.
Now, there aren't any industry-wide standards currently for testing LTE MIMO over the air. And so carriers have had to develop their own approaches for this. How do you see them grappling with this, and what are the approaches that operators are using to develop their own tests for validating MIMO at this stage in the industry?
Well, standards-wise, 3GPP and CTIA, they have been pretty busy over the past couple of years developing standardized set of tests for MIMO OTA. And mainly, there are two competing strategies here. One will be the reverb chamber, one will be the anechoic one. And as standards work on a committee basis, then it takes time for all the companies and all the participants in general to agree upon a standardized set. And so it's been quite a long time without getting to a finalized set of standards. But in the meantime, the world is moving ahead, and then each operator has been basically taking what they need or what they think is better for them out of these 3GPP and CTIA efforts, and then making them their own. And then at the same time, they are actively participating in promoting their own testing methods into a standardized world.
Okay. So two different approaches, and two different ways of approaching this problem. Maybe the two of you can talk a little bit about some of the complicating factors for MIMO OTA testing. There are two different approaches, I think, for some significant pros and cons, and maybe you can talk about some of the complications that OTA testing addresses.
Right. So each of the methods has its own pluses and minuses. So, for example, one of the complicating factors in an anechoic chamber type of MIMO OTA system or testing is the size of the device. So that particular method requires more transmit probes as the frequency is getting higher or the size of the device is getting higher. So that's some complication. On the other hand, reverberation chambers, the modes, the electromagnetic modes that they can excite within the chambers is directly related or inversely related to the size of the chamber. So as recently lower and lower bands were open for LTE, then this creates a bigger challenge for the reverb chamber testing.
Derek, any thoughts there?
Yeah, so what he basically means there is that as if wireless carriers want to operate at very low frequencies, then we have to build bigger chambers to accommodate the larger wavelengths that are occurring there. One of the keys to reverberation chamber technology is that it's very important that the phone sees a lot of different highs and lows in terms of power and direction and delay and other things in order to really develop that smooth statistical profile that we need to result in accurate average measurement solutions. And if the chamber as the chamber starts to get small relative to the wavelength, we can't fit as many waves in there. And it takes us a longer time to get really accurate average results and to really kind of fill the statistical profile of a test. So, so what we have done is we have a pretty good understanding of that relationship, and as long as the carriers and wireless network operators don't jump too low too fast, we can usually keep up with them without having to move too high in cost. For example, right now, a pretty typical low end of carrier operations is in the 700 megahertz area. And we found that works pretty well with a chamber that's about 6 feet wide and about 6 feet tall, and about 4 feet wide and 4 feet long. So kind of half of a typical engineering cubicle in terms of size. And that works pretty well for at the 700 megahertz range. And of course, it always works better at higher frequencies. In fact, the higher the frequency you have, it just becomes all that much easier to fit lots of those smaller waves in the chamber and get accurate results.
Okay. So we talked a little bit about the standards work that's still going on and the anechoic versus reverberation difference in the approaches there. Derek, I've already sprung this question on you before, but Alfonso, I wanted to touch base with you as well on whether you think it's likely that we'll end up with more than one standardized method when it comes to this kind of MIMO OTA testing.
I am 99.999% sure that will be the final answer. And the reason is that MIMO encompasses a wide variety of techniques that involve the use of multiple antennas at both ends. And some of them work better for higher scattering environments, and some of the others work better for not as much of a scattering. And therefore, as we were touching this particular topic before, anechoic chambers and reverberation chambers have their own strengths at different size of the scattering environment, And therefore, I fully expect that in the standards world, people will have to have some set for some techniques, some frequencies, and another one for another set of frequencies and techniques. So by techniques, what I mean, I can divide them basically in two broad groups. Some of them will be based on spatial multiplexing. So a larger scattering or a rich scattering environment is better for them. And the beamforming type of techniques that rely on not that high of a scattering or rich scattering environment. And therefore, more than likely, both techniques of OTA testing will end up in one way or another in a standardized world.
Okay. Derek?
I would agree with that. I think that there not only are, kind of these variations in terms of capabilities, but over-the-air testing, because it's a system test, it can get fairly complicated. Anytime you're trying to control microwaves in free space in the real world and not in the simulated environment, it can be a complex operation. And so because of that, as people try to trade off, say, flexibility versus complexity, as they want to trade off maybe cost for research capability and other kinds of those types of solutions, I really think that they will want to consider coming at the problem from different angles, just like Alfonso said.
Okay. So one final question. We're starting to see MIMO evolve. T-Mobile US recently confirmed that it is beginning to use 4x2 MIMO in its LTE network. And to this point, we've mostly seen 2x2. So as we move into some of the higher order MIMO arena, how do the testing needs or the approaches change?
For this type of, well, first of all, the reason why people are moving to higher and higher counts of antennas at both ends is because that is seen as a viable path towards increasing the spectral efficiency of the system. And therefore, we've been seeing a lot of companies beginning to explore even the 8 and 16 type of counts. And even handset, being size limited, is still working with 2, but we really do not discard the possibility that pretty soon we will go to 3, 4, and higher counts. So those will necessitate, again, depending on the type of MIMO technique being exploded at a given time, it will require a particular set of testing methods. So, but again, as we said before, if we go into 2 broad ranges or groups or categories of MIMO, which will be beamforming or spatial multiplexing, or in this particular case, a 4x2 is something like a hybrid. So you will get a little bit of both. Then we will have to look for the technique that is appropriate for the particular technique being used at a time. If it is going to be spatial multiplexing, then we will go for a rich scattering environment. If it is going to be sort of like a beamforming, then we will go for a line of sight and not as rich of a scattering environment. So these two, the increase of antenna counts at both ends will come with, or will bring about new challenges in the OTA world.
Derek, your thoughts?
It's really true, just what he said. Every time we expand the number of inputs and outputs on our base stations and on the phones, we basically, in order to simulate those, we have to add another measurement channel that occurs there. In theory and on paper, that's pretty straightforward. I mean, we've already solved the problem for 1 by 1, and you just solve the same problem again for 2 by 2. In fact, once you've done the 2 by 2 thing, you're already at a matrix of cross connections among all of these different inputs and outputs. And so now we just expand the matrix. Well, expanding the matrix in real life really means that now we're expanding the squared number of things that can go wrong as we connect all of these different things up. And one of the things that we really have to try to do is, in order to keep that manageable, is to start to really start to reduce kind of the number of things that can go wrong and the number of connections that can go wrong in there. Or we have to start to look at things over a wide range of variations and incorporate those variations, and if possible, cancel them out if they're incorrect. It's part of just the engineering of making something that looks pretty straightforward on paper work for us on a regular day-to-day lab kind of environment. And I think that we have a good start with what we've created so far with Spirent's VR5 and the reverberation chamber. The VR5 technology, I've already seen that they have the inputs and outputs that would be needed to handle something like the 4x2 MIMO that's described there, and our ability to put the right number of ports into the chamber so that we can inject those signals that are provided by Spirent is a relatively straightforward and well-accomplished path there. And then it's just a matter of getting the engineers who are working with this system comfortable with the fact that there's more going on here and there's more that can go wrong, and now we just have to solidify that and build confidence in the testing process over time. I really can't emphasize this concept enough that when we're dealing with something like MIMO and OTA, there's a lot of complexity and there's a lot of uncertainty because there's multiple ways that we could be doing things. And engineers are always second-guessing themselves a little bit. And I think it's very important for us to be able to provide a system to those engineers who are going to be using this day in and day out, where they can feel comfortable saying, hey, if I put this phone in and I go through these 3 steps, I'm going to get an answer, and that answer is going to make sense to me today, and a similar answer is going to make sense to me tomorrow. And from that, I can really actually just start to build insight into what it is that I'm trying to solve, as opposed to just introducing more uncertainty in this complicated world.
Okay. Great. Well, gentlemen, thank you so much. I've been talking with Derek Skousen, Technical Marketing Manager for Bluetest, and Alfonso Rodriguez, Senior RF and Systems Engineer with Spirent. Thank you so much for your time today.
Thank you, Kelly.
Thank you for having me.